So this lecture is on implementing the Chebychev. Okay? Now, it seems rather obvious why I might do this. Since homework 5 is there, and it says implement the Chebychev, and we haven't really done it. So today we're going to rock it, and we're ready from there. Okay? So that's what we're going to do. So just keep in mind, some of the stuff I talk about will be like as if, it's almost as if I should have talked with the other lectures first, but we'll pretend I just had planned this the whole time. Okay. All right, so let's talk about this Chebychev transform. A couple things to note. When we do Chebychev, and we're going to work with Chebychev, you are no longer working with equally spaced points. It's the first and foremost thing to know, right? You have your points x of j, and here is what your grid is going to look like. You are going to evenly space the points in the variable theta. And that's going to give you uneven spacing in x. And we'll see that in just a minute here. So j equals 1, 2, all the way to n. Okay? The other thing we want to construct with this is a differentiation matrix. I'm going to call this d of n. Okay? Now, of course, this is where, like, there was a lecture that would have, let's say, supposedly happened in the past, but it's actually going to happen in the future. Okay? We got a cell phone with some music. Dude, that's awesome. Is that Justin Bieber? Seriously? You know what? Did I tell you I hold you guys accountable for that? It's your generation. It's your fault. If you guys put Justin Bieber out there and he's like, seriously, what kind of haircut is that? Anybody under the age of 22, I hold you accountable. Okay, so some of you are safe and some of you are definitely not safe. I'm going to actually make it 23. Let's make it 23. Okay? So I get a few more people that I can blame. Okay, all right. He will not go away, nor will that bad hair of his. Here's the other thing we want, a differentiation matrix. What this so you've got to figure out is how do I differentiate, right? I'm now no longer on an even domain. I define things on some x now where I have clumping. Remember how this works. You evenly space here on an arc. That's my attempt at even spacing. And the x's then get clustered at the boundaries. Okay? And then you've got to figure out, like, I want to differentiate functions on this weird domain. Normally, when we did differentiation, right, if you did center difference, use your neighbors. And it was rise over run formula. So neighbor left, neighbor to the right, rise over run. And your run was always fixed, right? Your two neighbors were delta x this way and delta x this way. And your run was 2x, 2 delta x. Now, every point you go to has a different run on it, okay? Right? Because this delta x here is different than this delta x here. So we take care of that by constructing a differentiation matrix d of n, which basically works with the Chebychev polynomials to do differentiation for us. So pretend there was a lecture that happened, which will happen in the future. Okay. Probably Monday. Okay. So we're going to construct this, construct this. That's the goal for today, for implementation. Okay? All right. So let's go to the programming. All right. Here we go. MATLAB action. Okay, nothing like MATLAB action on a Friday morning to get you through the weekend. This is like, you know, pre-funking. Okay? Is everybody good with that? Is that kind of a good analogy? Everybody know what pre-funking is, right? Okay. I'm hoping everybody knows what that is. That's pretty sad if you don't. So first of all, I want a matrix D of n. So I've already actually provided it for you. So I'm going to go open it. You can just, I will email it to you later today, or you can just copy and paste out of the notes. And here's what this thing looks like. It's a fairly small little function, but basically what it's going to do is build for us these Chebychev differentiation functions. And it's going to be, the function is called Cheb, short for Chebychev, right? Okay? And all you got to throw into Cheb is the number of points you want. N. Kind of like the Fourier transform. You say, hey, look, I want to... Remember, it thinks you are working on a domain -1 to 1. That is just the assumption it makes. Okay? So you just say, oh, how many points do you want to slice -1 to 1 up in? You get to pick. You pick N. And what it's going to return to you are two things. D and X. D is our differentiation matrix. X are the spatial discretization points. Okay? And here's the code. Obviously, if you put an n equals 0, you're not discretizing anything. Okay? So it just returns n's. But if not, it comes through here. Notice the connection formula. X is just simply build it on a domain cosine pi times 0 to n over n. So here is your even cutting of theta, right? That's you're cutting the theta variable evenly there, and then you're projecting that even cutting onto the variable x. So we just generated x. Now the matrix C is a little more complicated, and that's what that does. We build the diagonals, off diagonals, and the lecture that we missed will tell us what's supposed to be in there, and this does it. Okay, awesome. So Cheb.m. Cheb.m. Remember that name. Okay. You'll be using it. Okay? So that's what Cheb.m looks like. Yeah.
So there's no like cliff notes for
Cliff notes?
does or later in the notes just to explain that, so we can go back and refine an explanation of these lines of code.
Yeah. In fact, the lecture I will give in the future, which was supposed to happen in the past, we'll explain what these things look like. Yeah. It's like, it's getting close to Christmas time, so it totally makes sense that I would talk about the future and the past and the present and all mixed up. This is what your life looks like without knowing what Cheb.m should be. Does it look bad, or is it okay? Okay. All right. Well, anyway, it's something. But Cheb.m is there, and that's going to be your main function call. This is what you're going to be working with all the time. You know how to differentiate things, and so let's just start off differentiating some things first. That's a good, fun thing to do. You take a function, differentiate it. Who wouldn't want to pre-func by differentiating functions? I don't know who, but I'm all good with this. So let's do the following. I want to take a function, and here it is. I define some x variable. Gosh, I don't even need these. That's amateur. Okay. Just take a function. U is equal to x. It's some random function. Okay? And what I'm going to do with this function is just say, well, let's first of all plot it. Oh, come on. There we go. Just to see what it looks like. Okay? So run. Boom. I got my MATLAB working, by the way. Nice. Ooh, ooh. I still got my buttons up top. I got my Java working. Sweet. Turns out, if you look hard enough on the net, somebody has a solution. All right. So there you go. There's my function. A couple things to notice. It is not periodic. Right? So if you were to FFT, you can differentiate functions as long as they're periodic. But it's not a periodic function. It's just some random function. I just want to calculate the derivatives of that function right there. Okay? Now, what have we done before? Well, what we've done before is finite difference. But remember, we're going to do this in a spectral way. In other words, we're going to think about representing this function in a Chebychev basis. The Chebychev polynomials, I wrote down the first 5 in class a couple lectures ago, right? You're going to take this function and represent it in that basis and take derivatives in that basis and then pop it back out. You're going to get spectrally accurate results. So if I were to do finite difference differentiation on this, and if I use a second order scheme, then if I use 0.1 as my dx, I would get results that are accurate to 10 to the minus 2. Whereas here, using Chebychev, I get spectral accuracy, which is beyond all orders accurate. So it's not delta x squared accurate, it's exponentially accurate. There's no algebraic power that captures it. So it's a much better technique in a way. Okay? So I have that function. I want to differentiate it. So first of all, I've got to decide, I'm going to start working with this thing. And by the way, I do have the actual derivatives here. Let me actually show them to you. Here's the first derivative of this thing. And hopefully I'll type them in correctly, because otherwise you lose a little bit of the show if you type these in wrong, because it won't look like you get the right answer. Here's the first and second derivative, which aren't not that hard to work out, but you know, in fairness, I could have probably picked a simpler function, but fine. It's not that bad. Okay, so now let's plot x, u, x, ux, x, ux, x. Okay, so I have function and its two derivatives. Okay, there we go, generic things like that, and I think they're probably right even. Yeah, it looks like they're right. So I want to just say, okay, now let's go use Cheb to calculate this. Okay? Calculate these derivatives and see how well I do. All right. Let's take this out for a minute. So now, first thing to establish, you are not going to differentiate on those points. See those points? They're evenly spaced. Your Chebychev will not want evenly spaced points. It's working with Chebychev polynomials connected through this cosine, which means you're going to work on this domain that's clustered at the edges. Okay, so that's the first thing. So that means we have to build a new x. Well, so you actually don't build the x. You just say, how about if I chop it up into 20 points? Because Cheb.m is going to do the rest for us. So Cheb.n works the following way. D, that's all I got to do. I send a number of points I want in the discretization. I get back the x domain. I get back the differentiation matrix. And there's going to be 20 points in x2. And I'm going to have a 20 by 20 matrix, D, which is my differentiation matrix. Okay?
Where does x come into?
This is just for us to compare to the exact solution. Right? So part of what we're going to do is when we go to plot this thing, we're going to ask, okay, how well does it do against the real solution? That's it. So this is just plotting my function and its derivatives that I know that are exact. Yeah.
Got a wider domain, you have to scale to the minus one.
Mm-hmm. Yep. So by the way, you've already done that. Anytime you use FFT, you have scaled your domain to 2 pi. That's what that 2 pi over L is for the K. And by the way, for your homework, you're going to have to do that. Should we talk about that real quick? What do I tell you to do in the homework? Hey, can we have the lights over here? Minus 10 to 10. I know it's easy to just ignore. I know it's easy to ignore a 0 because it's like 0. But negative 10 to 10 is what you're going to work on for your homework. This Cheb thinks you're working on some domain negative 1 to 1. So here, let's just call that C. So this is what it thinks you're going to work on. That's what we tell you to work on, right? You have this domain. So you're going to think, wait a minute, I gotta rescale this. Now, the way you did this in FFT, you ate this whole, you didn't even think about scaling. You just put a 2 pi over L. Maybe you didn't even think about what that meant. But now we got to think about what that means. What it meant and what it means. Past and future and present all together. Okay? So how do you make a connection between here to here? How do you rescale something that lives here down to something that lives here? Pretty simple formula. You say that something like this. C is equal to x divided by 10, for instance, will work. Because if I do that, when that's negative 10 or 10, it goes from negative 1 to 1. Sweet. I made the connection. So first of all, you got to do that with your initial data. Second, how does this impact derivatives? Uh-oh, you're not happy. I can tell you're not happy.
Well, what you would scale, because you're not giving
Oh, for this?
X anymore. You're just calling Cheb right away, and you're getting X from negative 1 to 1. So then you scale that to negative 10 to 10.
Yeah. Well, so in our homework, you have to figure out this is what you're getting. What you're getting out, but this is what you want. You want negative 10 to 10, and Cheb is not giving you that. Cheb.m does not.
So you have to scale your X output from Cheb to negative 10 to 10.
Mm-hmm. So it's easy to say,
Does the differentiation matrix want to work with negative 1 to 1? Or does it not
yes.
care?
It wants to work from negative 1 to 1. So this is where we have to make the connection. Because it's really easy to take this and multiply by 10, isn't it?
Yes.
Awesome. In fact, you just see it there, right? Multiply X. Awesome. I can just pull this X out, multiply by 10. Easy. But what does it do to derivatives is what matters. In particular, if you remember, I have u of x. For instance, if I take a function, take its x derivatives, and now I'm going to a new variable c. If you remember your chain rule says, everybody agree with that? Okay? Working some chain rule magic. C of x is? All right, hold on. So that wasn't supposed to happen. Okay. That wasn't supposed to happen either. Okay. Sorry for you people at home. I didn't mean to drop you. All right. All right. So hold on. That was for emphasis on the board, and I got a little carried away. Okay, we're ready. Ready? Okay. So we can do this. That's 1 over 10, isn't it? Or more generally, if this was L, and that's L, that's your transformation, right? And so this gives you 1 over L, u of c. So if you're making a transformation, you're going to be working over here. So think about your equation. Your equation is the following. Let's take a heat equation. ut equals uxx. This is on domain negative L to L. When you call Cheb, it's on this domain. So when you start using the Cheb and its differentiation matrix, you've got to go, oh, look at that. I got this. And I'm actually working with those variables. And I can make a transformation over to here by rescaling. But then every x derivative picks up a 1 over L. And so you get this 1 over L squared. See that? That's your rescaling. Make sure to put that in your problem.
But if you scale your X out to the minus 10 to 10, so when you make your initial conditions and then you plug that in,
That's your derivative.
but you're...
We'll talk about it afterwards. But you have to have that scaling. 2 derivatives. Each derivative pops 1 over L. Right? This is 1 derivative. I got 2.
Yeah, but
Right?
when I differentiate u of x, again, don't I just go 1 over L times u del
U of x?
u-
I can, u of x is u of x, x.
Right,
That we already said was c of x.
right.
That's the 1 over L. So now, but I still have that x there. So I'm going to have to replace that x by another one. All right. Called busting heads. Forearm in it. That's right. I see in the back. Don't forget the forearm shiver the problem first. If you don't do that, you will not get score later answers. Okay. Everybody good with that? Well, everyone's not quite good with that, but it leaves you something to ponder. The pre-funk isn't going quite as well now, but that's okay. We're going to play around with this. Here. All right. So first of all, let's forget about scaling and just simply work with this function, which is in fact defined from negative 1 to 1. And when I get these things out, here they are. x2 is my grid. Those are my points, 20 points in particular that I've picked. And differentiation matrix D. So gotta like that. So what I'm going to do now is go ahead and say, okay, let's make the function. And first I'm going to do is just, I'm going to subplot these up. And we're going to plot x versus u, which is my exact function. We'll make that a black line. And we'll plot x2 versus u2, which is my Cheb. And we'll make those magenta circles. So first, let's just do this. Okay. There's the function in black, like on the interval, which is just discrete points. And then the magenta circles are the Cheb points. Now, a couple things to notice. Look at the spacing here at the edges. Look how close these are versus how spaced these are. Okay, so there's your clustering that happens. High clustering on the edges. In fact, look how close these 2 points are here. And it gets further away, and then in the middle, fairly evenly spaced clustering again. Everybody go with that? Okay, so that's what you see if you're going to be using Chebychev polynomials, clustering at the edges. Which again, if you have stuff going on at the edges of your domain, it's quite nice. Okay? Now I want to compute derivatives of u2. So I want like the first derivative, which is just that. So let's do subplot 3, 1, 2, plot x versus ux, and we'll again make that a black line. This is our exact answer versus x2 u2x. Okay, so there's our first derivative. And look at that. Doesn't care if it's periodic, spectrally accurate solutions.